To the Bangalore Theory Seminar. Our speaker today is Professor Prahladh Hastad. He's a professor at TIFR. Before that, he was a research professor at TTIC, and he did his postdoc at MSR Silicon Valley, and he did his PhD from MIT, and his master's too. So his general area of research is complexity theory. He has mostly worked on this PCB constructions and circuit complexity. And today is going to talk about the criticality of AC0 formulas.
Can you hear me? Thanks, Harsha. Thanks for inviting me. Happy to speak at the Bangalore Theory Seminar. I encourage people to come a little forward if you can, because I'm going to be writing on the board. I don't know. I might start big, but I might eventually shrink. Size as you can come as forward as you think you're comfortable.
I think I muted, I know. Yes.
Get started. Okay, so we'll be speaking on a recent result of ours with on criticality of AC0 formulae. This is joint work with two of my students, Tulsi Mohan Molly, who's graduating shortly, and Ashutosh Shankar. So this topic is related to trying to understand the limitations of computation and computation models. This is a general theme in complexity. We would like, there's an underlying model of computation. We would like to know how best we can do this, what sort of lower bound we get. And we are pretty dismal at this. Complexity has not managed to, the upper bound side, it has fancy algorithms, the lower bound. To understand models of computation, there are very few models of computation for which we really do understand them fully well to say this is something you cannot do in this model. And one of the sort of most minimal models is the model of shallow computation. That is, computation in which it's not very, the depth of the underlying computation is not a very deep network. In fact, most deep networks today are actually fairly shallow. I'll come to those topics later on. So this is notion of computation using via shallow networks. So what do I mean by this? And all my talk today is going to be focused on certain specific models in this model of computation. I'm asking for certain powers in this model. Okay? And the two central characters in our story today will be, which I'll define shortly, will be what are called AC0 circuits and AC0 formulae. So what are these two objects? By the way, feel free to stop me at any point of time. What I would like to do for the large part of the talk is just to talk about the statement of the result we are proving. I'll spend a fair amount of time building up the statement, why this is an important statement, why it's an interesting statement, and time permitting, in the last 20 minutes or so, come to how we managed to prove this statement. So what are AC0 circuits? So we're trying to model computation using circuits. We have some Boolean function. So we say we have some Boolean function f on n bits. And I want to build a circuit that computes this function. And we're going to allow the circuit very minimal functionality. We're just going to allow the circuit to have AND gates, OR gates, and NOT gates. That's all. This is a universal set of gates. You can compute any function. And you're going to ask, compute a circuit, come up with a circuit using just these gates. Now, even these gates are not fully specified. You must tell me an AND gate, what's its panel, an OR gate, what's its panel. Is it an AND gate of panel 2, panel 3, and this one? If you want to be realistic, you have to have bounded fan and AND gates and OR gates. But we'll give it a little more power. We'll talk about unbounded panel, AND gates, and OR gates. We're going to talk about circuits. So we're going to the AC0 circuits. are basically circuits composed of built with AND, OR, and NOT gates. The NOT gates, of course, are fan in just one. They negate an input. But these both will allow fan in unbounded. The fan in can be unbounded. And because now we allow the fan-ins to be unbounded, there will be some more things we can do. We can push the NOT gates using De Morgan laws always to the bottom of this one. So we'll assume that the NOT gates are always at the bottom of the circuit. And because you're alternating, we can because we have unbounded fan-in, we can always assume that two ANDs one AND doesn't feed into another AND. You can always merge the two ANDs with each other. So you have ANDs and ORs alternating in the circuit. And in fact, that's the reason for the name. These are alternating circuits. Precisely for that, we're going to have a bunch of literals at the bottom, variables and their negation, followed by a few AND OR gates. Reverse, you alternate and you keep on doing it till you complete the circuit. So that is what our main model computation is going to be, AC0 circuit. So you have some underlying circuit. You have same. Let me give examples. That's a thing on 4 inputs or 2 inputs, X and Y, that I'm allowed to use the negations of the inputs. This is one function. Another example of another function is example of yet another function. Here the gates all have fan in 2. Here some of the AND gates are fan in 3, and examples of some gates. And so these are what are called AC0 circuits. These are actually some of these. So the underlying model is a DAG, and what the root is computing is actually the final function. Yes. Now, the two functions which I drew, the circuits which I drew here have yet another property in them, in the sense that it's actually a tree. Ignoring the fact that in the bottom, here it's a perfect tree actually. Here that some variable is being used twice here. Let's ignore the fact that variables or literals can be used multiple times. If this is actually a tree. If this object that we constructed were a tree, we will call this the formula. AC0 formula, the special case of circuits when the underlying circuit is a tree, but here I will ignoring the literals at the bottom, ignoring the repetition of literals. And what we are generally interested is how good, give me a function, how well can we come, what's the best AC0 circuit that I can come for this, what's the best AC0 formula that I can come up with for computing this particular any function that I care about. Now, the moment I talk about best, there's some underlying parameter of the function that I care about. So what are the functions? What are the parameters? First thing we care about is the depth of the circuit. How deep is this circuit? That is, we'll ask what's the number of alternations between AND and OR? Do we go from the root all the way to the leaf? So for example, this is a depth 2 circuit. It's a DNF. The form thing being computed is both these are depth 2 circuits. It's a DNF. A vanilla AND or OR will be a depth 1 circuit. More complicated circuits will be larger, deeper circuits. So ANDs and ORs are depth 1. CNFs and DNFs are depth 2 and so on. Okay, so that's one parameter. We would like to ask how deep is the circuit, and the shallow comes from the fact that in general we'll be talking about circuits which are not very, very the circuits and formulas which are not taken. The next thing is, of course, how large is this circuit? How many bits? Now you want to measure the size of the circuit. So depth is one parameter. The parameters of interest will be depth is one parameter. The other one will be size. Size, yes. Size, yes. There are various measures in which you can count the size of the circuit. Typically, it's counted by the number of wires in the circuit. We will slightly follow a non-standard model. It's be useful the way to represent our result. What we'll talk about is the size is going to be the number of bottom ands or ors in the circuit. For example, this one is 2. It has 2. The bottommost, it has 2 ands in it. This has 4. Therefore, size of this is both these are depth 2 circuits. This is a size equals 2 circuit. This is a size equals 4. We'll soon see once I state the results, it will be easier to work with this. This is certainly a lower bound on the more traditional notion of size, which is the number of wires. Okay. Huh? I am going to use this for both formulas and circuits.
Can I not see like at the bottom I create a dummy gate in which 2 x's are feeding, 2 y's are feeding. I will just manage with just n gates at the bottom.
Then how does that help you?
If you're going to be counting only the bottom level,
yeah,
increase the depth by 1 and make it 2n or something, the size.
But then how
Maybe
no. So I will. Okay, technically say it should be a non-trivial and or. It should be a non-trivial and or will be my, and it will be a non-trivial and or. Yeah. Okay. Something which just feeds an x will be counted as just 1. If we x and x, all the ands and ors by necessity should actually have been. You cannot feed 2 variable twice. Okay. It's just going to be easier for me to represent it that way. Use it. The actual definition you'll have to use wires. Okay, so these are our characters. We have these AC0 circuits, AC0 formulae. Would like to find out how good these objects are. So we're going to test them against something. So our adversary throughout this one will be the parity function. We are given a function on n bits, which is basically counts the number of ones in the input. And we want to ask how well can we compute parity. So we're going to test this object. So we have the whole this table will summarize the sequence of results I'm going to be talking about. We'll be looking at AC0 circuits and AC0 formulae, and we'll keep testing them against parity in various senses of the word. How well they can compute parity in this sense, how well I'll be listing out this, how well they perform against parity. And why do we choose parity as a function when looking at these low depth circuits? Parity by inherently is counting the number of ones in the input, and parity seems to be involve counting. And if you look at it, counting is actually, you can't do counting in a very think of writing circuits for counting. You don't expect to be able to count in shallow depth circuits. It requires at least depth log n. In fact, the way if you are going to do counting, the way we count, if you're going to count from left to right, actually it's a depth n circuit. You want to do by sort of a efficient counting in which you can try to get log n. Anything which involves counting is not going to, at least informally, is not going to be doable using a shallow circuit. And that's the reason why we are going, and because our models of computation are fairly shallow, d will not be too large. D will always be a number less than log n throughout this one. Parity is something which these objects are not going to be able to compute easily. And question is, how well are we able to compute it, is what we're going to be looking at throughout the lecture. Questions? So let's start off with some basic stuff. So yeah, so everybody knows what parity. Let's look at size bounds. Size bounds. And let's start with the simplest case, b equals 1. So what can you compute parity using a depth 1 circuit, an AND or a OR? No, a parity cannot be computed by an AND or an OR. So these are actually it's not doable. But the moment now let's get to depth 2. So now I'm asking if can parity be computed by CNF or DNFs. In fact, any formula can be function can be computed by CNF DNF. But let's ask what's the best function that can compute parity of n inputs. Guesses for this? How big? So I'm just asking you, can come up with a CNF that computes parity, or come up with a DNF that computes parity. For instance, these two things which I drew here are actually this is parity of 2 bits, this is parity of 3 bits. So how would you? Yeah, so exactly. So one way of looking at it, notice first thing, in any of these CNFs, once you set suppose it's a DNF, once you set these 3 variables, these 3 literals to true, the formula fires to this one. Therefore, all the bottom ANDs should be sort of a setting such that it fires the parity to 1. Now, parity cannot be set to 1 unless you set all the variables. So firstly, you know that if it's a DNF, each of the ANDs should involve all the n variables. In particular, each of the ANDs involved will only have one setting in which parity is going to get set to 1. There are 2 power n minus 1 settings in which parity goes to each. So in particular, the number of ANDs involved will be 2 power n minus 1. So both in the CNF and the DNF case, you can show that it is 2 power n minus 1. Well, and depth 2 formulas and this ones are the same. Formulas in AC0 circuits are the same. So you have a depth 2 circuit which requires 2 power n minus 1. What we said actually this is both a construction as well as a lower bound. You can't do anything better than this. And this is exactly what is the implementation of what I just said for the case of parity of 2 bits, parity of 3 bits. What happens if we go to depth 3? Can you do any better? Certainly these are depth 3 circuits also, but now if you allow myself one more layer, can I do compute parity slightly better than?
Parity of the first half and the second half.
But the first half is already 2 power n by 2. So okay, it's the exponent from n has gone down to n by 2. But you can do exactly something like that. Parity of n bits can be written as the square root n parity of square root n parities each. So parity can I don't know. I can't. This one? Yeah. So we can write a CNF out here. So let's plug in a CNF that computes square root n parity and another CNF that computes. Actually, it will be better to. So this will be an OR. This will be, suppose this is a DNF. I put an AND of ORs. It's in our favor to put an OR of ANDs here so that you can merge the OR and OR, and so that you don't get an addition of depth to 4, you actually get a depth 3 circuit. If you stare at this object, you will see that for depth 3, what we'll actually get is 2 to the, so it will be some order 2 to the square root n size object you get for n parity. By the way, is this construction that I gave actually a circuit or a formula? More than ORs merging. So suppose I take, let's try to compute parity of 9 bits by imposing this with each other. So now here, so this x and this x I have to feed in the same. It's the same thing. So that there's a gate which is going to have a fan out of 2. Therefore, the construction which I gave is actually going to give me circuits and not this one. To actually iterate for general D, what we can observe is this construction will give you a 2 to the order n to the 1 over D size circuits. In general, if I extend this all the way, but this is a circuit construction. It's not a formula construction. Formula, you'll have to now repeat these objects. If you're computing, this is a parity of size 3. The same parity of size 3 is being used twice here. You'll have to recompute it in the formula case. And when you unravel it, what you'll get here is it will blow up by an extra factor of D in the exponent. That D over here is what will be the difference between when you blow up a size S depth D circuit, it will become a size S to the power D depth D AC0 formula. T minus. So all of these are all D minus 1. Yeah, for 3 it was square root 2. So for depth D plus 1, let me write it. Yeah. Okay. So depth D plus 1 we have that. So size bound. But the argument we gave here the argument when we gave for depth 2 was both an upper and lower bound. Question is, do these upper and lower, do we also have lower bounds? Do we know? This is one, we saw one way of constructing parities, both the formula and circuits. Question we can ask is, can we do better than this? And we haven't been able to do, and it was asked and was done, and this is where research in the early 80s focused on this and tried to ask, can we compute parity better than this for shallow depth circuits? And one of the, so if you want to understand a question like this, first thing you want a tool, a technique to separate parity from low depth circuits. You're going to say, I'm going to apply this technique which says parity will still remain a hard function, whereas low depth circuits sort of simplify. And what was observed is there's this tool called random restrictions. And it's not hard to see that this is going to be extremely powerful while analyzing and OR gates. What's a random restriction? It's just a partial assignment. It's an assignment of the n variables to 0, 1 and star. And what's random about it? The random part will be, that is for each I. So it's going to be a random, I'll call it random restriction RP, where P is a number between 0 and 1. For each I, row of I will be set to star with probability P and 0 and 1 with probability 1 minus P by 2. Independently. So for each variable, you toss a P bias coin, and if the coin comes up heads, you pick it to be, you let it remain unset. Otherwise, you uniformly flip another unbiased coin and set it to be either 0 or 1. So, and why is this a useful tool? Why is the notion of random restriction useful when comparing AC0 circuits against parity? You notice that when we hit parity with a random restriction of this type is going to, on average, leave P and variables unset. Parity on P, even if you restrict parity, it will still remain parity of P and variables, or possibly the negation of parity of P and variables. But an AC0 circuit, in this AND, if I feed in even one of the variables has got set to 0, it will destroy, it will annihilate this AND. So random restrictions have the property that they will kill ANDs and ORs very fast. So the circuit will simplify extremely fast, whereas parity still remains more or less unsimplified. Therefore, if you can show on a random restriction, your massive circuit becomes a DNF, and while parity still remains, at DNFs we have this lower bound, and we can invoke this lower bound. So the notion of using random restriction, by the way, this is not since almost in the birth of circuit complexity, since the late 60s or so, random restrictions are being used to study the power of circuits, because we know that random restrictions kill AND and ORs, whereas most functions are not so easily killed by AND. But they were specifically studied for the sake of size lower bounds of AC0 circuits and formulae, starting from the 80s by the seminal works of 4 stacks and successor. So first stacks and successor in 84, followed by I showed that parity cannot be computed by any AC0 circuit of constant, of poly size and constant depth. And their main tool was the notion of random restriction. And we wanted to further understand this, and then there was subsequent work by Yao, Bopanna, and finally it comes a, in this context, sort of the knight in shining armor was the switching lemma proved by Johann Hastad in 86. So he used a particular property of DNFs and CNFs from which one can actually prove that these bounds are actually optimal. You can't actually do anything better than these bounds. So these actually, all these bounds turn to be theta bounds. And the main tool is the techniques. Sorry, not over here. Only for the circuit space. And this was proven by Hastad. So what is the switching lemma? The switching lemma which sort of got these exactly proved that you cannot, we saw a construction which achieved 2 to the n to the 1 over d. And the switching lemma, using switching lemma, you can prove that you can't do anything better than this. So let's see what the statement of the switching lemma is. The switching lemma is this following statement. It says, let f be a k-DNF. And what do I mean by that? It's a DNF in which the bottom ends have Fanon utmost k. That is, bottom Fanon is less than or equal to k. And we hit f with a random restriction rho coming from R, from one of those, and we ask how does this simplify the DNF? What they show, what the switching lemma says is, now notice if you take a DNF and if you want to convert it to a CNF, it's going to explode. The size, when you do this De Morgan's, size will explode. Switching lemma says that that's true in general, but the restricted formula actually has a very small size CNF. The probability that it will have a large CNF is very small. In fact, it doesn't talk, and in fact, this is the reason why it's called the switching lemma. It switches a DNF to a CNF, and vice versa. It switches a CNF to a DNF. What actually the statement shows is actually a stronger statement. It shows not just a CNF version of it, but a decision tree, which I'll shortly say what it is. The decision tree depth, in fact. The probability that the decision tree depth is larger than t is at most pi p k to the power p, where dt depth is depth of best decision tree. A decision tree is this natural thing. You query some variable. If it's 0 or 1, you then based on adaptively query the next variable and go on, and you ask what's the depth of the most, or how deep is any such decision tree that computes parity. Notice that if you know a decision tree, you can also compute a CNF and DNF. What switching lemma says is the statement of this one. It says you have a f which is, as a DNF, if the bottom Fanons are all small, it can be a very, very large DNF. But once you hit it with a random restriction, the probability that it requires, that the restricted formula requires large depth is really, really tiny. It's exponentially tiny in t. The larger t becomes, this is going down exponentially. So once you choose speed to be something like 1 over 10k or something, this is going down exponentially small with the depth. Now this seems like a, okay, this, I don't know, face of it, how interesting the statement is, but this switching lemma, of course, besides proving the optimal lower bound over there, sort of what considered one of the gems of theoretical computer science. It's led to a huge industry of results since then. For instance, one thing which we can do from the switching lemma, we can bound the Fourier tails of AC0 circuits and stuff. And once you know how to bound the Fourier tails, you can use these to learn these circuits. So the seminal result of linear Mansur-Nissan, the fact that AC0 circuits are learnable, you can shallow circuits of ands and ors can be learnable fast, derives its entire existence, owes its entire existence to the switching lemma. The switching lemma is a very, very powerful statement that has been the center of several results in complexity, and it basically tells you what happens to a DNF when you hit it with a random restriction. Any questions on this? That's the switching lemma, and the switching lemma was central to prove this statement. This upper bound which you showed, it shows that this upper bound is in fact tight. And this was a state of affairs for a long while. This is how it was.
Yeah, this is tight. There are k-DNF.
For that one, so there are two things. One is the switching lemma statement itself tight? Yes, the statement itself is tight. Modulo this constant. I don't know whether it's E, possibly E can. Hastad in his paper says that this constant can't go smaller than E, I think so, but this is a constant we get in this one. But it's also tight for this reason. It gives you this tight number here. So if it had a better number, you would get something even larger than this, which you know you can't, because you haven't matching upper bound over there. Okay. Questions? So that's the switching lemma statement, and it led to this tight bound over here. This is ET6.
In some sense, this is tight this bit.
The switching lemma is significantly stronger. It shows much more stronger results than this. It was stated for that, but the primary goal was to prove that, but it's a stronger statement than that. It's a stronger statement than that. And we'll see what is stronger about it, and you'll also see there's something weak about it, and that's what the result, what I'm going to talk about is going to come. Notice I had this other thing also over here. I said AC0 formulae, I had a construction which gave 2 to the d n to the 1 over d. I erased it. That was an upper bound construction. Now you can ask whether the switching lemma, this proof which Hastad gave only a lower bound for AC0 circuits. It did not yield, of course, it yielded the same lower bound for AC0 formulae also, but the question is formulae should have even a better lower bound, given that. So certainly formulae also, this will be the same proof will show that it will be 2 to the omega d, omega n to the 1 over d. Question is, can you put in an extra d in front of it? And this took actually a long while. Till, I don't know if this question was not asked earlier or not, but till Rossman in 2013 actually showed that even that one is tight. And his main tool was once again the switching lemma. The switching lemma was the heart of his proof. He used the switching lemma. So when Rossman showed in 2013 that even the formula lower bound that we had over here, by the way, this is a stronger lower bound than this because this lower bound implies this lower bound. So Rossman in 2013 showed that in fact even for formulae, the switching lemma can be used to show a tight lower bound. Okay, so that seems like the end of story, but we can ask more things about how well one can compute. So let me erase this. So these are talking about, I want to come up with a circuit that exactly computes parity. Many a time. Sure.
So, are they non-uniform versions of this?
These are non-uniform. These are by, what do you mean by non-uniform?
So, I was wondering like if certain variables show up more often than not in the.
These bounds, lower bounds hold even in the non-uniform setting, non-regular, non-uniform setting. They are, in fact, that's what makes it. These are, I don't follow, it's a.
Non-uniform from a computational point of view.
Yeah, you're talking.
Uniform is what? Do all variables appear uniformly often at the bottom?
Right.
Or
Or not it's on average it's the degree of the box. It's not k-DNF but much smaller.
No. So this statement, for this one, you can show that there's an equivalent statement here in which, so what is this stating? This is stating I have a DNF, which is an OR of ANDs, and these have fan and K. And the amazing thing is this, it doesn't put any restriction on this fan.
And I'm saying, imagine that the bottom K was on average.
So that's exactly what I'm going to. Okay. I don't know how much should be. I am fine, but I do not know if I caused an electrical disaster over here. Hopefully not.
Nothing happened.
Nothing happened.
Nothing.
I take those wires also.
No.
Yeah. Sorry.
He says theory is not impactful. I've seen water spilled here before, so
Should be fine. Just leave it. I think it should be fine now. Just leave it.
So this result more or less holds as long as, so what you're asking question is, do you need the exact bound on K or something larger than K? So there's an equivalent result which shows that if things are very large, if the panels are very large, notice that those gates are basically useless because they're very high probability it's going to be killed by a random restriction. So only gates, so gates which are too small don't contribute, will not find how large is this. If K is roughly more than log m, you can just ignore the gate in this one. So this result, even though it doesn't depend on m here, you can always assume that all the K's here are smaller than log m. And that's how it will be applied in those results. Okay.
So when you said using the switching lemma, you meant black box or you modify the proof?
No. You use the switching lemma. All of these proofs use switching lemma as a black box. This is the statement they use. Everything, the very few, we'll come to where I'm going to use switching lemma non-black box, but all the statements, both Hastad's proof and Rossman's proof, use the statement and then complete the proof. Those two lower bound proofs. Okay. So what we're talking about, so these are talking about size lower bounds. Now you can ask about more interesting things. That is, I come up with a circuit that says computes a function. It might not compute it exactly, but it might compute it 90% of the time. Even then, it's a good enough circuit. Question is now you can ask how well can you compute in this way? How well is your circuit correlated with parity? So you can ask for correlation results. And what is correlation? So correlation between I have two functions f and g, both Boolean functions. And what we are asking is the correlation between f and g. And this is precisely the probability on a random input x, f of x equals g of x. This is, but what we'll do is we want to measure this quantity, but we'll subtract probability f of x not equal to g of x from it. Therefore, if f were a random function, then if f were a random function, then g should get a correlation 0. The probability that it computes it should be exactly the probability it does not compute it. And this is, if you notice it, this is just expectation of the f of x and f of x times g of x. If you write f and g not as 0, 1 functions, but plus minus 1 functions, then it's exactly this quantity. It's a nicer expression to work with, where f tilde, g tilde are plus minus 1 valued functions. So now what I would like to ask is I would like to do the same as for size lower bound. So size lower, let me write down the depth d plus 1, we had this was due to the omega n to the 1 over d. This was due to the omega d n to the 1 over d plus 1. And both of these are via the switching lemma. This is Hastad and this is Rossman. So now I can ask what is the best correlation with, I give you a size S and a depth d plus 1 AC0 circuit. Ask what's its correlation with an n bit parity. So we'll ask correlation bounds now. And this question is actually formally asked by Rahul Santana in 2012. So he asked what's the exact, and he conjectured it, looking at previous upper bound constructions, conjectured a result which the previous results did not prove yet. So we could get some correlation bounds from the switching lemma, but they did not use the optimal, that is, they did not match the corresponding best upper bounds on it. So there was a whole, several people who worked on it. So starting with the work of Dean, Prahladh, Srikanth Srinivasan, Harsha, Matthews, and Paturi. They came up with various, using the switching lemma, they came up with various improved correlation bounds. And then Hastad actually in 2014, he looked at the switching lemma proof in a non-black box fashion and came up with what's called, what in today's language, which we call the multi-switching lemma. And got the correct bound here, which is 2, which the correlation is 2 to the minus, let me write it as just exponential in minus n over log s to the power p. Notice if s is 2 to the n to the 1 over d, then the correlation will become 1. S was 2 to the n to the 1 over d, this gives this number. Therefore, if I had such large size, I have perfect correlation, and this sort of nicely interpolates all the way from, you have a polynomial size circuit, it has an exponentially small correlation with parity, and it interpolates correctly all the way to the right lower bound. So this was sort of an extension of this lower bound, but it also proved a correlation result. And what is the multi-switching lemma? So let me state the multi-switching lemma, but to state the multi-switching lemma, it will be useful for me to introduce another notion called criticality. Yeah.
While natural like this correlation has connections to other like functional measures, like for example, like does it say something about the Fourier spectrum?
It will give you. So I'll give another definition which will give you even more natural and tell you you'll get Fourier spectrum results. I'm going to just give you a second. So we'll define another notion called criticality. Comes to the title of my talk, criticality of a Boolean function. So f is once again, as always, f is a Boolean function. The criticality lambda f is defined to be the minimum lambda greater than or equal to 1, such that the following, such that if you look at probability, it's going to be completely inspired by the definition, by the switching lemma. I'm going to hit f. I'm going to hit f with a random restriction, random RT restriction, and ask what's the depth of the, and ask exactly the same statement. What is the probability that this restricted guy has large depth? This should be less than or equal to p times lambda to the power p for all t. So that lambda is called the criticality of the function. Notice, just observe that the criticality of a k-DNF is by Hastad switching lemma, this is at most pi k. It's just the extension of what Hastad proved over here to an arbitrary function. This was only for k-DNFs. So I'm defining criticality as it is that number which controls how small the decision tree becomes. The probability of large decision trees when I hit the function with a random p restriction. Now, why is this useful? This is useful for all sort of reasons which Prahladh was critical. So once you have a criticality statement, you have the following immediate consequences. Consequences of criticality. One, the decision tree size. This is not the depth, but the size. It's the number of leaves of a decision tree of f is at most order 2 power 1 minus 1 over 2 lambda n. So the smaller the criticality you get, sorry, it's at the smaller the smaller the criticality, you get better decision tree depth size response. Correlation of that function with parity, it immediately yields correlation bounds. It tells you this is order 2 to the minus n over lambda. It gives you exponentially small correlation depths. Then going to thus one, it tells you that if you look at the Fourier spectrum of this function and look at the tail, that is, you're looking at all s's, so that mod s is greater than or equal to k. We're looking at a Fourier tail for some arbitrary k. This is at most 2 times e to the e power minus k by lambda. Therefore, the smaller lambda is, you get a better bounds on the Fourier tail. This is the L2 Fourier tail. You also get things for the L1 Fourier tail. So this f hat s, not tail actually, is just size of all s, mod s equals k. This happens to be less than or equal to order lambda to the power. And these results are extremely powerful because once you have criticality bounds on a particular function, you have Fourier tail bounds. This tells you the class can be learned fast. These tell you that these were studied. L1 Fourier tail comes to construct pseudo-random generators for these. So once you have criticality bounds, you have all of these consequences immediately. And this notion of criticality was defined by Rossman in 2019. It's well after Hastad. So Hastad proved this in 2014. But it's easy to state the multi-switching lemma in terms of criticality rather than the way Hastad originally stated it. So the original states the multi-switching lemma statement. So the proof of this is switching lemma. The multi-switching lemma statement is just the following. The multi-switching lemma in terms of criticality. This says f is a size s. Depth is computed by a size s, depth b plus 1 AC0 circuit. Then lambda of s is less than or equal to order log s to the power, which is exactly what does. This plus this correlation consequence will fetch this result. So this is restating Hastad's multi-switching lemma in the language of criticality. And once, so criticality not only gave you correlation bounds, but it also gave you this. So there's not an answer to your question that correlation implies this, but I think this simple result implies these, but there's a more basic result which actually implies the Fourier tail bounds that we carry. Okay. So that was out here. Now, once you have this picture, now one obvious question is what's happening here? What is the criticality of AC0 formulae? Certainly, it is at least this. It's at most this. But AC0 formula possibly you can even do even better criticality bounds. Therefore, the conjectured bound here, because immediately after this, it is conjectured that if F is a AC0 formula instead, of size S and depth D plus 1, then criticality should be order log of S by D the whole power. So which will give you correlation bounds, the exponential minus n by which will say that if I get this number and plug it in, it will exactly give me correlation 1 and S was of that size. This was the conjectured result. And so Rossman defined criticality, and this precisely to prove this, what Rossman managed to prove this was, so Rossman in 2019 proved this only for regular formulae. And regular is in the sense that if you have an AC0 formula, the Fanon at every level is the same. That is, all gates at depth I have the same Fanon. It's a very regular. Notice the formulas which we constructed are very regular. All even the recursive constructions would have been very regular, but not all formulae that you construct are regular. For example, even as simple as you want to take two n-bit numbers, take two numbers which are n bits each and add them up. The corresponding formula that you write down for addition will not be a regular formula. There will be some, because of carries and all, so it won't be a regular formula. The gates won't all have all gates at the same level won't have the same Fanon. So there are times when you need non-regular formulae to construct. So the example I gave doesn't tell you need it. Is the most obvious construction requires is irregular. So now you can ask, is this bound true even for a non-regular formula? And that's basically our result. We prove this result for all formulae. So our main theorem is basically this statement. This is the criticality of AC0 formulae. And the reason this number is interesting, so particularly, so we prove this statement, which would imply the corresponding correlation. So this is HNS for all formulae. In some sense, it's a sort of the strongest bound written on this. It implies all the other four bounds written on this, all the other three bounds written on this. And in particular, the main theorem which we have, this criticality bound implies the switching lemma, the multi-switching lemma, all of them it will imply this result, yielding you the right result for AC0 formula. Yeah, so that took me most the entire allotted time to tell you what the statement is. Take some questions and then give you a 5-minute thing of what goes into the proof. Yeah. No, it didn't. Even for regular case, it did not yield. Regular case. So, in fact, the proof didn't. All of Hastad's construction, all the constructions over here, they were a very bottom-up construction. And if you're doing some proofs which are bottom-up, you cannot distinguish circuits from formulae. Formulae to circuits, you have to do the proof top-down. You have to realize, and you're splitting the whole thing into smaller parts. If you're doing a bottom-up thing, you cannot distinguish between formulas and circuits, and all these proofs had a very bottom-up flavor to it. Rossman's proof, the regular case as well as ours, is a very top-down proof, and that's the reason why we are able to get the right bound for formula. To my knowledge, you can't do anything. You can't get anything better than what you get this for. This one without the improved statements for the formula from you just using the switching lemma. Of course, the Rossman's this proof just uses switching lemma, but It's a very clever application of switching lemma in a top-down fashion. Questions? Sort of give a.
How critical is it to have this for like all T and not so? I mean, there are like similar but hard enough, right? This is like a Gaussian tail.
So the point is, once it begins, exactly that will happen. Once you have it for a particular T, it will begin having it for larger T, just the binomial distribution itself. Once you have this, you will begin proving it for larger T. So this such a statement is sufficient if you know it for certain values of T. For instance, I think the right value of T to prove this is when T is something like log S is what's the right value for which I care for. If I manage to prove it for this, the same proof will sort of lead. Either the same proof, I do not know if the proof black box leads, but at least the same proof will yield the statement for all. Yeah.
Like, so in a 5 K case,
Yeah.
Like in the k-DNF, there was some intuition. The intuition was that if you have an of K, choosing T which is proportional to 1 over K, you will start hitting most of them.
Yes, if you have a K, if you hit slightly larger than 1 over K, everything the union bond will tell you. In fact, this was Bopanna's original proof was based. Bopanna proved the statement for monotone this once, and that was the intuition, and he put it, and Hastad basically extended it to all formulae this one. Now the question is, what is this corresponding number? So in the case of DNF, it's clear that the criticality is like 1 or it's theta 1 over K. In fact, your bound can be said that it cannot be smaller than theta 1 over K. You can show that you cannot do better than 1 over K, and Hastad switching lemma shows that 1 over K is sufficient, possibly slightly larger 1 over, possibly larger K is sufficient. The question here is, you can ask, why is this number an intuitive number?
Yes.
So why is log S over D? And I think those will come with. So I don't have a straight answer this one. If you look at the Fourier tail of these ones, that's where the Fourier tail sort of tapers down. It sort of criticality immediately implies this. So we had these, at least experimentally, we had these for AC0 circuits and this one. So that told you that that's the right number to go for. So actually, till I think till about a decade ago, because Rahul asked this question, we did not understand this. What is this right? What's the number you have to hit a function with so that it becomes a low depth decision tree? This is criticality, and this can change. Even for as simple things like AC0 circuits and formula, it took us only till recently do we understand what this number is. Yeah.
You have like a sense of the family of Fs for which this is somewhat tiny, for which criticality is close to log.
You're asking, so this is certainly for AC0 formulas of this. You're asking what's a larger thing? I don't know. So this is no. So this is where shallow circuits, these are saying they can't compute a lot. But you can, so they can't compute parity. A similar line of results shows shallow circuits can't compute majority. So now you can think of adding majority and parity to your shallow set. Now instead of having and or of gates, you also add parity gates or threshold gates into the circuit. And suddenly the game becomes, now you're basically shallow circuits with the threshold gates are every deep network that you're talking about is basically this. It's like a depth 5 network with some threshold gates. And we really don't understand these objects. Even depth 3 threshold gates, we have no idea what they do. We don't have, even forget about correlation bonds. We don't even have the lower bonds for these. PC0 at this one, and that's precisely why this whole field, the deep networks, these are actually just deep. When they mean deep, they mean depth 3, depth 4. That's all they mean over there. And once you add threshold gates, they become extremely powerful, and we are very far from understanding the power of these objects. I think I will. Do you want me to? I can spend 5 minutes talking about what the proof of O. So I'm going to rewrite the statement in a slightly different language, which will then lead to the proof of it. I can do that in 5 minutes, or I can conclude right now. I can do either of them. Okay, so let me do that. And in fact, what I'm going to do is going to just rewrite the criticality statement over here in a slightly different language, or actually it's not slightly stronger statement of it. It might seem like the same statement, but I'll tell you why it's a more powerful statement. And in fact, while we were working on it, we have been working on it for several years on this project. It took us at least 3 years to get to this statement. Once we had the statement, it took us 2 weeks from the statement to complete the proof of to finish the proof of this one. So the statement and the definitions involved here are the hardest part. So what do we need to show? We need to prove the following statement. We need to prove that F is an AC0 formula size S and depth D plus 1. Show probability, and I hit it with an RP restriction. That's what, just read it in the statement. So I need to show that any decision tree, the problem is that every decision tree requires, even the best decision tree requires large depths, is very small. So what we will show, this is also for Hastad proof, we will not show any decision tree, we will build a specific decision tree. For every formula, I tell you a canonical way to build a decision tree. We will show with high probability this decision tree itself will be very small. So the first thing will be, I won't have time to define how we do it. We'll talk about a canonical, the first thing is we'll talk about a canonical decision tree. If I prove this for this decision tree, this is certain, certainly will imply the other one, because even this decision tree I say is going to be small, is going to be a low depth decision tree with high probability. Therefore, the probability that the others will be low depth is even better than this. That's the first thing which we've changed. This. We have to define a suitable notion. This, I don't have time to go into this, but there's a suitable notion of canonical decision tree. Now we're going to analyze this event. How does this event work? This is a bad event, and I want to bound the probability of this event. So in this scenario, you can say this bad event happens. So there is the way the decision tree will first will suppose F is F1 or F2. It's a formula. It's an OR of several FM, which each of them are ANDs of several objects. This canonical decision tree would have first built a decision tree for F1, and then under it, it would have built a decision tree for F2. Under each leaf, it will then build a decision tree. There will be something very canonical about this. This is how it will go around building this decision tree. Is in natural fashion, you first find out what F1 is, then for every leaf of F1, put a corresponding decision tree for F2. So there will be a decision tree for F2 sitting under each one of these. Then put a decision. That's how the canonical thing will work. So if I have to have a long decision tree, I must have a long path like this. F1 should have had a long decision tree. F2 should have had a long decision tree. Fm should have, or at least whichever Fi's come in this path should have had long decision tree. So I would like to break up this event into the AND of several events. So this is one bad event E1. This bad event E. I'm going to write it as the AND of several events. Now, when I want to do this, typically, so I want to bound the probability of E. Each of these events will look like same things for smaller depths. So I would like to write it as probability of A times probability of B, and then use induction to do the proof. Unfortunately, this is not a true statement. These events are correlated statements. So what I can at best write is probability of A conditioned on this is true fact. I can first write, but now so probability of A is like a smaller event which I can possibly use induction. But this becomes really a nasty event now to work with. That is, I'm asking this event happens given that the other event has happened. So these things become extremely cumbersome to work with. Question is, how do we handle such objects? So what we will show, we'll actually not prove this statement. We'll actually prove a stronger statement than this. We will show that let F be any down closed set of restrictions. What do I mean by that? It's just a set of restrictions, partial assignments to the n variables. A down closed set means if a particular partial assignment is there, any further refinement of it is also there in that set. What we'll prove is that the proof we have actually proves this stronger statement. So it not only what we'll prove the stronger statement, that is this event even conditioned on F. And the way we break this event so now I have to actually be bounding E given F, which I'm going to write it as probability of A given F times probability of P given F and A. We have to do this. The way we will write down A and B will be such that A will also be a downclosed set. So F and A will just be another downclosed set. Induction will apply and you can complete the proof of this. So what we notice is just there's a stronger statement that actually the people is proving. That is not only proving this statement, it's proving the statement even condition on the fact the restriction belongs to a particular downclosed, any downclosed set of restrictions. And once we do that, we are able to handle these bizarre conditioning statements that we wanted to handle, even though they go downstairs and cause really weird events, because the statement is actually stronger than what we want to do, it actually handles. But this requires more care than what I said. You have to choose the events A and B very carefully and done. It took us a long while to come up with the statement, but once you come up with the statement, it's not hard to complete the proof of it. I'll stop with this. This has been a bit vague. I'm happy to answer questions after.
Yeah.
Since you mentioned majority,
No, majority is very well correlated with an and, no? And or an or. So they have 1 over square root and correlation. So
the worst case lower bound.
the worst case lower bound, but the correlation wise majority is very well correlated with these objects. So you don't get good correlation bound. Parity is something. The point is, parity has this feature that even if you know only t variables, if you know the value of t variables and n minus t is not known, you have no correlation with parity. Whereas majority, if you know the value on some variables, it gives you a hint about what's going to be that. So possibly the thing to do about majority is, if you're working with a uniform distribution, correlation was defined based on the uniform distribution. That's a really bad distribution to be tested. For parity, that was a right distribution in which you are checking. There's no reason why you have to check it. Correlation has to be defined on the uniform distribution. There might be a harder distribution in which you want to do, whether it's a natural distribution or not is unclear. But you might have to work with those distributions. There will be harder distributions for majority than in the case of parity was nice because the uniform distribution was the hard distribution for parity. Majority that's not the case. It's actually the uniform distribution ands and ors correlate quite well with majority. There are other distributions where you'll have to do it. So these won't be correlation, but it will be mu correlation. That correlation is defined based on that distribution. Even the constant function with majority. Yeah. It has inverse polynomial correlation.
Thanks again. we have a small
You have copy and check answer. We got it.
It's like how much we just random distributions and neural networks and see how we correlate.